Welcome back. In today's episode, we'll discuss extrusion, sweeps, and lofts as ways to create surfaces and Breps, starting from the NURBS we discussed last time using Grasshopper and Python. Check it out. We are in our Rhino environment. Let's create an extrusion first. So we do extrude here, and we need to specify a profile and a direction. So an extrusion is a curve. So C extruded along a vector. So we need, in this case, let's do the Z vector. So just unit Z. There it is. And then let's specify a curve. Let's draw it directly in Rhino, which could be maybe this one. There it is. And then we have an extrusion. Let's maybe specify a different height. Let's say maybe, I don't know, 8 meters. Okay. And then we have an extrusion. We can also extrude open curves. We could do a polyline, for instance. Let's try to do a polyline like this. Maybe move it to the left so it's not overlapping. Okay. And we could also extrude a NURBS. So let's do a similar shape, but with a NURBS. Okay, there. So it's a cubic in this case, and we can extrude all of them. We can just overwrite this curve and provide a list, and we get 3 surfaces out. So what is happening behind the scenes? Let's check the surfaces. So if we bake it, and then we go back to Rhino, let's start from this last NURBS. As I said, we were starting from a cubic. So as you see, it has four control points, and the same thing holds for this surface. If you turn on by going under surface tools the control points, you see what it did is it took that vector which was 0, 0, 8, moved all the control points to that position, and then just created a surface in between. The same thing it did for these 2 surfaces, but if you try to inspect the control points, it will not work. It cannot turn on control points for poly surfaces. So what you can do is you can exploit them, as these are multiple surfaces joined together. And then for each one of them, you can turn on the control points individually, and you can also like move them around, and you can see that these points are actually controlling these surfaces. So what's happening is, again, here, these points, this point, this point, and this one, they just took the base curve, moved all the points by the vector we specified, and then created a surface in between. So this was extrusions, which is the simplest way to create NURBS surfaces from curves. So let's now go. Let's maybe delete these extrusions. We don't need to bake them. Right. Let's go back to Grasshopper and see sweeps, which is the second way of creating vectors. Actually, before we see sweeps, let's see the same thing, the same extrusion with Python, so you can see that it does the same thing. So let's just create the same component maybe. So let's go base, and let's go direction, and then we can go extrusion as an output. So extrusion there. And then we can say the base is a curve. So we can specify that curve, and direction is going to be a vector. So let's go there, vector 3D, and we can say they're both required. Maybe the direction is not required. Whatever, let's say it is, so that it doesn't run if we don't specify the inputs. And let's also drop in our inputs, so the same ones, and let's hide these extrudes so we can see the result of this extrusion appearing automatically to the left. So we import Rhino geometry as we're used to, Rhino geometry as RG, and then we say extrusion equals Rhino geometry dot extrusion. Extrusion. All right, and then within the extrusion class, there's a static method called create, and this create will take a curve, and then we'll extrude it up. So we can do it 2 ways. One is supplying the curve, which is base in our case, and a height. It will infer the direction of the vector from the plane in which the curve lies on. Let's try to do that. So we'll do base, and then height, it was 8 meters in our case before, so 8.0, and then false is cap. We don't want to close the extrusion at the top. I mean, for this one, we could close it at top and bottom, but let's not do it at the moment. So this is one way. We are not using direction in this case, so let's actually use this direction input. There's a second way we can call, in which we can call the method, which if you go, let's see if it shows me. If you go to the second method, it will show that. Misclicked. All right. We supply the curve, a plane, so the plane will determine the normal direction, and then the height again, and then if to cap it or not. So let's pass in the base again, and then we need to create a plane. So let's create it here, so it's easier to understand. So we do plane, and this is rhinogeometry.plane, and then plane has a static method called from normal, which we discussed briefly in one of the previous episodes. And then we can pass in an origin. In our case, we don't really care about where the origin is, so let's just throw in the 0, 0, 0 point, so Rhino geometry point 3D, and then we'll just do 0, 0, 0. Okay, and then as a normal, we'll pass in the direction we defined before. Okay, and then we have a plane that we can pass to this one, which defines the direction. Then we have the height, and then we have, I'll just run it so that it gives you an error, so that the preview goes away. And then if you provide all the correct inputs, you see we get the same result as we did before. And of course, we could say that cap is actually true, and in case the extrusion creates a closed loop, so or in other terms, in case the base curve was closed, we get a closed Brep, which is basically a solid representation. Okay, so this was extrusions. Let's now do sweeps. So for sweeps, let me delete everything. We'll create something new from scratch. Let's delete this as well, and then we can do maybe a beam. Okay, so this was a typical example of a column. Let's do a beam. So what's a sweep? So a sweep. It's an extrusion of a section along, this time not a direction, but a curve. So we could do maybe a curve like this. Okay, this is the axis of the beam. Let's say we have a curved beam, and then we want to have a section for this beam. So let's say the beam is this cross section, and we want to sweep this one along that one. So the rail will be a curve, which we can simply select, this one. And you may be tempted now to say, well, the section is a curve as well, so we could just take the section, select it, and click, and then drop it in. But you see, this actually doesn't do what you think it would do. So to do that, you actually have to take this one, align it to the section first, and then once you aligned it to the rail, you can sweep it along. So let's do that. To do that, we'll do orient, which will take a curve from a source and put it to a target plane. So the geometry to move is this profile of the beam of the section. Then we do the source, which is just a plane. Let's set it in Rhino, so set one plane, and we'll set this plane over here. So this will be our insertion point for the beam, or maybe even better, let's do like the middle axis. So we'll do this as the source, and then as a target, we need a plane which is perpendicular to this curve at the start of the curve. To do that, we go with a perpendicular frame. We need one perpendicular frame on the rail. So this is the rail. We put it here, and then we need a parameter. This parameter is the t we were discussing last time in the NURBS video. So it's 0 because we want the rail, we want the start of the path. And now that we have that, let me preview this off, maybe these off as well. We have this plane. Now there's a problem that you can check out, which is that in this case the section has the horizontal axis, which is the x-axis pointing to the right, and then the vertical axis is the y-axis pointing up. But you'll see that in this plane, x is correct, but y is pointing to the wrong direction. So it's pointing down, we want it pointing up. Otherwise, it would flip the section to the wrong side. In this case, it's not very evident because I put it in the middle, but if it were maybe something like this, you would clearly see that it's above or below the rail curve. So let's fix that as well. So to do that, we need to flip the plane, which is this plane we got here. So this is the frame, and the parameters we need to set are booleans. Sorry, not this one, boolean toggle. So we don't want to swap the axis. So let's say to false, but we want to swap the y-axis because that was wrong. So that's true. And then if you hide this one, you see how it's correct. And then you can take this one and put it into the target. And indeed, now if you inspect this geometry, you'll see that it moves this curve to the start of the rail. And then you can take this one, put it to sections, and indeed we get the correct sweep we were expecting from our modeling before. So let's now maybe cap it. So there's a component to cap that as well in Grasshopper, which I haven't shown you before. And there it is. We have a beam. Now this has a slight problem, which you may encounter if you try to model actually beams, but maybe mostly roads, bridges, stuff like that, because when the path is not horizontal. So let's try to move it. So if I move this point up, you'll see that this tilts around. In case the profile has only 3 points, the plane will be determined by those 3 points. But if you get a lot of points, let's try to create something more complex like this one. You don't have a clear plane in which that happens, so that will stay maybe flat at the start. And then if you change maybe only the last one, you see the start point is unaffected, but then this endpoint, let me curve it even more so it's more apparent. These endpoints, maybe let's drop this down a little. Okay, you'll see this endpoint is not vertical anymore. Like it's slightly tilted to the left in this case. We could even make it more evident probably by turning it like this, moving it up. Okay, now it's more evident. So, and this maybe you don't want. You want the top plane of the elements to stay flat, basically. And the only slope should be given by the change in section, cross section, and not by along the rail because of you moving around the rail. So how can you fix that? Well, you can fix that with a loft. So there's in the API a thing called road like, but it doesn't which is a parameter of this sweep, which is not available in the components, but still it's not great. So let's fix it. So we'll fix that with a loft, but we'll see that in a second. Before we do that, again, let's do in Python the simple example of the beam. So let me try to do that again. So I'll just select this one. Okay, we just want to reproduce actually. Yeah, like this. We just want to reproduce this beam in Python as well. So let's do Python. And for the sweep, what we need to do is we want, let's see, a rail and sections. This meter is just telling you how it has to connect different curves. So let me try to add. Let's say we have a polyline instead of having this NURBS. Okay, let's put in there. it should be more evident in this case, apart from the rotation of the plane, which in this case it's probably not to be switched in that way. Okay, yeah, like this. The meter is this the way it's joined at the vertices. So if we change the meter type to maybe rotate or to none, so if you go to rotate, you see it changes slightly, and if you go to 0, it will not join them at all. So it will create 3 separate Breps. Okay, so this is the meter, and so now let's select back this curve. Okay, and do it in Python. So to do it in Python, we need, well, we'll skip the meter, we'll just give it a constant. We need the rail and the section. Let's call it rail, and then let's call it section. And then this will be the sweep. Let's call it sweep 1 because there's a sweep 2, and we'll check it out in a second. So we have our inputs. Actually, we have provided those, so let's drop them in. So the rail is the same as this one, so let's drop in the rail, and the section is the same as this one. Let's drop that in, and we can also tell him maybe it is a curve like this, and this is also a curve like this. Okay, what's it's complaining about? Oh, I selected circle instead of rail. It's a curve. Okay, and then we can do the same as before. So we can import rhino.geometry as RG, rhino geometry, and then we can have sweep 1 equals rhino geometry.brep dot create from sweep. There it is. And then these are a bunch of ways you can create this sweep. I believe the first one is the easier, so let's use this one. So we'll do rail, then we need the shapes, which is a list of sections. So in our case, it's, we only have one section actually, so I made a slight mistake. So right here, we have to say this is a list. It will be a list of only one element, but it's indeed a list. Okay, and then I forgot what it needs. So let's see if it prompts it to me again. So it's rail, section, and then whether to close it. Okay. So in our case, let's say false. So we don't want it to cap. And then we need a tolerance for the sweep because it may need it in some cases because it's not maybe perfect. In our case, it will be perfect because the shapes are well behaved. So let's just use the document tolerance. So this is Rhino, a Rhino doc, I believe. We need to import Rhino though. So let's do import Rhino. Let's maybe create another variable, so called tolerance, which is Rhino dot Rhino doc active doc tolerance model absolute tolerance. There it is. So this is the tolerance, and it's the one set in Rhino right here. So if you go to the unit settings, you'll see that it has an absolute tolerance. In our case, it's 1 millimeter, and we'll use this one to provide it here. Let's drop it in and save it. And indeed, you can see from the greenish color that it's the same exact result. And we have now made a Brep as an untrimmed surface. You could bake this as well, and you see it's exactly the same. There may be something weird with the visualization because there's when you create Breps, you can actually fix the vertices, but we'll see this in a future episode when we discuss previews, because this creates problem with previews when you create plugins. So let's not see it right now. Okay, so this was sweep 1. Let's see sweep 2 as well. I'll just show you in Grasshopper with the components. It's quite easy. Well, maybe create 2 rails, and then we can extrude maybe a curve in between these 2 rails. Let me create a curve like this. Okay, and like that one. And let's say we want to create a surface which is this curve extruded along both of these rails. So this will contain the surface. This is used for maybe freeform roofs or stuff like that. So let's check that out. You can do sweep 2, and then it asks 2 rails in this case, so 1 and 2, and then a section which I already put connected in the same position, so already positioned correctly. So I don't need to orient it anymore. So this is rail 1 and rail 2, and then a section. And you see, indeed, we get this this freeform surface. And if we make, let's try to push it up a little. Yeah, there. You see, it also has a difference in height. So this also has a parameter uh, called same height that you can drop in, and it will try to make it flat at the top. But still like respect the 2 rails and the curve. All right, so this was the sweep along between 2 rails. This is probably quite used in architecture or in maybe car modeling, not sure. In engineering, it's civil engineering, at least I rarely see this used. But it's still here, it's very useful, and Rhino is one of the few software that can actually handle this, this stuff well. And of course, you could do the same thing with sweep with Python. Instead of just using create from sweep, there's a create from sweep with multiple curves, I believe. So let me go to the API, so I'll show you. Rhino common. There it is. Rhino common API, and we can look for sweep, and there's actually create from sweep. It's probably easier. There it is, create from sweep, and there should be within them the possibility to supply multiple rails. Yeah, in fact, there it is. You can supply 2 rails, a shape, and then the same parameters as before. So it's pretty easy. Let's make that as well. So instead of only rail, we have rail 1, and then we have rail 2. So we'll do this is a curve as well. Okay, and then we need to supply the second rail, the first rail, and the section. There it is, and now we have to provide this these to the functions, so rail 1 and rail 2, and we should get the same results. Let's turn on the preview, and indeed we get the same result. So this was how to do it in Python. The last thing we're missing is a loft. So what is a loft? It's a connection between multiple curves. So in this case, we don't have a rail to follow. We just have control sections that are ruling how the surface works. So I'll show you. It's easier to understand if you see it. So let's delete this stuff. It's not necessary, and let's keep this beam example because I want to show you how to fix the rotation, which is to do with the loft. So let's delete all this stuff. We don't need it. And for the loft, there's the loft component, of course, and it asks you for curves and options, which are optional. So let's not supply them. We'll see them. We'll see them later. So what are these curves? Well, ideally, we want to take this section, put it along this curve, but instead of putting it just at the start, we want to put it along the curve multiple times, and then the curve will be ignored completely, and just the sections will be used. The result will be actually the same, but yeah, you have control over the single sections, so you have the ability to change each section individually, whereas with the sweep, you have only one section which is extruded, so the cross section is constant. In our case, we can have non-constant sections. So let's actually do that. So let me create 2 different sections. So let's say we have a section at the middle, which is higher, and then it will go back to be smaller like this. So we'll have maybe 3 sections or maybe 4. The first one will be small, the last one will be small, and the 2 middle sections will be big. So let's do that. So we'll do perp frames again, and we'll select the curve, which is the rail we want to use. So this one, and then we want parameters where we want to put stuff. In our case, we don't really know the parameters. or because we have to supply the t, we know the length. Let's say we want to do the beginning, the end, and then divide the length in 3 times, and then put the planes at those locations. So we can do that as well. So let's do get length. I don't remember how it's called. Let's go to curve, evaluate length. Yeah, right. So we take the curve and then we say length. So in our case, we want the length of the curve. So that's the length of the curve in this case is 32 meters. So let's drop that in, and we get the parameter normalize is false because 32 meters is not between 0 and 1. So let's say a Boolean toggle false for that. There it is. And we get a point at the end and the parameter of the point at the end, which is 33. We could also supply 0, which will be the start. So we get both parameters, which is 0 and 33. And if you drop this in, you see we get 2 planes. And then we also get maybe the points as a quarter distance and 2/3. Yeah, 2/4. Sorry, 3/4 and 2/4. Okay, and to do that, we want to take the length and divide it by 4. So we take the length, we divide it by 4, and then this is the first point at 8 meters, and then we can just maybe multiply this by 2, and we get the other point at 16 meters. Okay, so then we can go 0. Let's merge them so it's easier to understand. So we'll merge 0 with the points at 8 meters, the point at 16 meters, and the total length. We don't need these 5th inputs. Let's drop those in, and we get indeed the parameters. So this wasn't by 2. We need to multiply by 3. Yeah, okay. So yeah, pretty much we could do we could also use the correct division using counts, or instead of supplying this divided by 2, we actually need to divide by 3, I believe, and then do 2 here. Yeah, okay. Now it's correct. So now we have our planes. Again, we have the same problem before, which the y-axis is pointing down. We want it to point up, and the fix is the same as we did before. So we flip the plane, we provide this plane here, we swap the axis. We don't swap the axis, but we swap the y-axis. Okay, like this. Now we have these planes, and we can supply. Well, we have a list of planes now, and we want to place, we orient the curves there. So let's take the curve. This is the target. The source is, we need to set a plane as a source. So let's set that. So plane. Let's go set one plane, and we go here, and can't select this. Why? Okay, like this. So this is the source plane. And then we want to place this to a target. Not all the planes. We actually want just the first and the last. So let's do first one and the last one. So first and then the last. Okay. But I want to this is the first plane. Why I don't get it? Oh, I haven't supplied the geometry, right? So let's do curve, select the curve here, put it there. Okay, now we have the geometry there. Let's try to put all the planes in and see how the loft works the same as before. So now this is very similar to the sweep. We get basically the same result as before. What we want to do now is to change the 2 middle section with a different curve. So instead of placing the same one curve in all the planes, we'll do it by hand in this case. So I'll just drop this in, select a second plane like this. Okay. And then as the target to be the middle planes, We could do this more programmatically, but for this example, it's fine. So let's do 1 and 2 as the index of the two middle planes, which goes in here. So now we have, well, let's actually do it with only one orient component using lists because it's easier. So we'll need a list item. We'll need a list of the planes, which is this one and this one. So this is a list of planes. We need a list of the curves. So this is the first curve and the second, we don't have it. So let's take it. So here we have the curve. We can drop it in. Fine. And then we need a list of we have a list of source planes and a list of target planes. We have it already. And then we can take the planes in order, in the correct order. So we want, in case of the curves, we want the first curve, then the second, then the second, then the third. So this is a way to select with multi-line data, the correct curves. Then for the plane, we want the same index. And for instead these ones, we need, well, we actually need all of them. So we don't need to worry about this list item. Okay, we should now see the correct sections positioned. Let me see, source geometry. Well, we have to plug in the correct geometry and the correct source planes. Instead, in fact, we do have it now. And now you see we have a first section, which is this height, then the two middle sections, which are higher, and then the last section, which is smaller. And we can't do this with the sweep, but with the loft, we can. All right, so now we have these curves. Let me show you the options, what they are. So loft options, and we can drop this in. So these are the options. And then let's start from, well, closed means that if you want to connect the first section with the last one, which usually gives weird results in this case. It's not an example where this makes sense, but you can close it. So if you have a sort of a loop, like a circle, you can do that. Adjust means that, well, let's show that with an example, maybe with a circle. Let's create one circle and then create another circle here. Let's move it up. Okay. And you can inspect the seams of these curves. So you can go seam, curve, seam, and take a look where it is. So you see the seam of this circle is up here. And then you can do the same thing for the one below. And you see the seam is down there. So these seams are not in the same location. And indeed, if you try to loft these objects together, let's try to do that. So we'll take two curves, take the curves, two curves. Okay. And then you try to loft them like this. You see this creates this weird result because the seam is not in the right, in the same location. But if you provide options and you say that adjust should be true, the Boolean toggle there, and you drop in true in adjust, you see it will take the seam of the first one and like make it so that also the second one has a seam in the same location, so the loft works properly. Then rebuild just takes the curves and rebuilds them with a certain number of points. So in this case, I say 3, like only 3 points are used to approximate the curves, 4, 5, 6. So like this is what it does. So this is useful maybe if you have polylines with different number of points, because lofts don't behave very well if you provide curves with different number of curves, with different numbers of control points. You can do them, but they produce weird results sometimes. Refit is the same as this fit curve here. So whenever you rebuild a curve, or you can decide if you want to fit it strictly to the old curve or not. So that's sort of the idea. And this gives you the tolerance of that refit. So the point has to be exactly on the point, or if you can move them around slightly, to create maybe a better smoother shape. And then the type, which is probably the most important. Let's see it again in action with the bridge deck example or the beam example. So let's say this is the type. So you see it's an integer between 0 and 5. So let's create a slider between 0 and 5. Actually, 4 it's not available, but between 0 and 5. So 0 is normal. We'll go back to normal later on. Then we have loose, which uses the points of the sections, the control points of the sections as the control points of the NURBS. I'll explain this better. If you take a look at the sections we had, so these ones, let's bake them. Let's hide these maybe. Okay, and we can get rid of that. You see now we have this section and these 2 points, of the section. When you do loose, if I bake this, and you take a look at maybe this, we explode it, and then we take a look at maybe this bottom curve, and if you inspect the control points, you'll see the control points are placed exactly at the section vertices locations. So loose means that instead of using of passing through the points, it's using them as control points. Is exactly the same as when you do a NURBS like this. So you define the control points, okay? Or let's actually draw the points first. So we draw the points first. You can create NURBS by using these as control points, and you'll see that most of the control points will not be part of the curve. Or you can use, and this is the same as doing loose when you do the loft, or you can do this one, which is passing through the points. So it will generate new control points so that the curve passes through those points. And this is the same as using, it tells you when you draw it. So chord spacing. So this is the same as using, let me go back to Grasshopper. Type. This is the same as using the normal. So the zero type here. So 0 is the one, and 1 loose is using control point. Tight is again using passing through the points, but it's using a different parameter here. So instead of using chord, it's using the square root of the chord. So I'll show you what it does. There you see this one, it's tighter, but what it means is that, well, we said last time that when you draw a NURBS, you have a parameter t that is going through along the curve, and you can imagine that t as time, so the time it takes to go between a point and the other. So if like in this case between these 2 points, this curve is shorter than this one, so it means that this curve it takes less time to go between the 2 points. So this chord or square root of chord are telling you how the speed is distributed along the curve. So in this case, the first case, it's using chord. It means that the speed is proportional, or it's distributed proportionally to the distance of between the points. So like this, let's say the distance between the first and the second is 1, and then the distance between the second and the third is 4. Okay, so it means that it's taking 4 times the time to go between point 2 and 3. Then it goes to go between point 1 and 2. Okay, with square root of chord, instead of being proportional to the actual distance, which is the chord, it's proportional to the square root of the distance. So you can imagine, again, with the same example, if the distance between 1 and 2 is 1, the square root of 1 is still 1, but the distance between 2 and second point and the third point, which was 4, the square root of 4 is now 2. And so now the time it takes in the second step is just twice the time it takes for the second one. Instead, before it took 4 times the time. So that's because the curve is tighter, because it tries to go in a quicker way between the points, using the square root of chord as a way to compute the parameterization of the curve. So this is the distance, the difference. The effect is just that it looks straighter, but not quite straight. So let's try to take a look. So if you go 2, I believe is tight. Yeah. So if you take a look between that, let me check. Let me delete the old one here. Okay, so this is tight, and you can check the distance, the difference with 0. And sometimes you can see it, sometimes you can't. It depends on how the surface is made. In this case, it's not very apparent, but it was more apparent here. The distance, the difference is this one basically. Also in the 3D element. And then we have straight. This is pretty evident because straight just does basically a polyline between the points. So it's exactly like if in a flat case you do this one. Okay, it's just a polyline passing through the points, but it's doing it in 3D. And then you have the last one, which is uniform. And what is uniform doing is, it's creating a NURBS that is passing through the points. And after it does it, it normalizes the knots. So if you recall from last time, we discussed the knots briefly. So you can create a knot vector. And let's take a curve. Okay, so let me delete this for a second to explain it. So we can create any curve between the points. Let's take this curve here, and we can inspect the control points of the curve like this. And you can also inspect the knots, and you can take a look that these knots are non-uniform. So this is a NURBS, which is non-uniform rational B-spline. The non-uniformity comes from these knots having this weird numbering. If you have it with a normal spacing, normal parameterization, you would get the default knot vector. So what the default knot vector looks like is you have to provide the number of control points, which in this case is 6. Let's say 6. The degree of the curve, which in this case is 3. And the knot vector of a uniform curve would look like this. So let's see if we make, instead of this one, actually let's create a new one. If instead of that one we create a new one, but by knots we select uniform, and we do the same, it will look very similar. But if we now do the same thing and inspect the knots of that curve, they will look uniform, and indeed they do. So you see they look like with the default parameters, which means that like you have repeated 3 and 0, which means the curve it's passing and starting from the first point, and you have only one times repeating the nodes in the middle, which means it's passing through those as well. All right, so this is the explanation of these types for the lofts, which are directly derived from a single curve NURBS. And you can also take a look in the API. If you do loft type right here, it will describe what I told you briefly, but it will describe these kind of types. There was developable in probably version 5 of Rhino. It's not available anymore, so this does not work in Rhino 8. So ignore it. And yeah, this was Lofts. Let's do a loft with Python as well, just so we complete the lecture. So we will take as input directly these curves already positioned, so these ones, and everything else we can assume it's an input. So let's preview that off. And yeah, there we have it. Okay. So let's do this loft. We don't actually need that one. We can hide it. So let's go Python, and we need curves to do that. So let's say curves, and that's the only actually required input. So let's do loft, and we can connect those. We can tell them it's curves, and we can tell them it's a list of curves. And then quite simply, we import Rhino geometry again. So import, let me zoom in so you can see better, Rhino geometry as RG, and then we do the loft, and the loft will equal Rhino geometry.brep, and then we get create from loft. So it's pretty simple, from loft. And this just takes in a list of curves, which is what we already have. And then a start point and an end point. We don't really need it, so we'll just do Rhino geometry dot point 3D dot unset, which is passing in basically an empty point, because we don't have to specify that one. It may be useful to specify it. This is basically the seam of the curve. It's telling you where, it's telling him where to put the seam, but in our case, they're already properly drawn, so it's not necessary. Okay, and then the loft type, which is well, just a loft type. So Rhino geometry dot loft type let's do straight because it's quite evident. And then closed, this is again, if you want to cap it or not. Let's say, no, sorry, no, this is if you want to connect the first curve to the last one. We don't want that, so let's go false. And there it is. So we have our loft straightly defined, and you can of course change this maybe to normal, and what you get is a more curved shape. And yeah, there it is. What else can we do is we can cap this as well. So this, I haven't shown you how to do it before, but there's this is a list of Breps. So you can have 0, you get just 1 Brep. It's just a list of 1 Brep, so it's not really necessary. Yeah, you have to do it because of the way the API is written. So now this is a Brep, and you should be able to do cap planar holes. I'm not sure if you can. You should be able to. Let me inspect this loft. So let's say print the type of loft. It should be a Brep. It is a Brep. We should be able to close that. So loft. I don't remember exactly. Let me go back to the API. Cap planar holes. There it is. And it's cap planar holes. We have to provide the tolerance to it, and it returns a new Brep. Yeah, a new Brep. So we should be able to run it from here. Cap planar holes, even if it's not suggesting anything. And the tolerance, let's just drop it in with a number this time. And yeah, indeed it works. It wasn't like suggesting it. And now if you bake it, you see you get a loft, which is capped at the start and at the end. I will just briefly discuss the problem we had before with this curved rail, and then we'll wrap up. So the problem was that if I open that up, let's create a loft maybe with yeah, actually this example works as well. We would like for like the curve to be curved, so not in a plane, but have the sections stay vertical, which is a typical example. So as I said, you can do it with a sweep. There's you go to sweep, the create from sweep. There's an option to do that, which is called road-like normal, and the sweep frame road-like, but it doesn't work that well. So if you use a loft, it works better. Well, the only thing you have to keep in mind is that here, well, you have the planes, you have to straighten them up. So we'll just put some blocks in here to straighten them up. So what is correct about these planes is certainly the z-axis. So we'll deconstruct this plane and get the z-axis, and the origin is also correct. But now we want to create a new plane. So create plane, and the new plane will have, oh, no, not really, plane. It doesn't let me create the plane. Let me go and check that out. It was deconstruct, no, create, construct plane, okay. So it has the same origin, and then we have to specify a new x-axis and y-axis. We already probably showed this in the example for planes or for vectors, but I'll just mention it again. So we can do a cross product. a cross product between the z-axis here and the global z-axis, and this will get us a new vector which has the z-axis, so the vector along the curve as the first vector A, and the z as the second vector. So this will be an horizontal vector always. And indeed, if you drop that into the x-axis, you get the thing maybe flipped, okay, in the opposite direction. So let me hide this one. So now we have the planes which are sort of correct in the x-axis, but we need the y-axis not to be the old z-axis, basically. So to do that, we do another cross product, because now we know what the x-axis is, because we already computed that. And we know what the z-axis is, because we said the z-axis was already correct. And so this gives us y, so z times x gives us y. And now these planes are all like the y-axis. It's not rotated, it's always vertically oriented. And now if you provide this as a target, this will create a new loft, but it's always using it's always oriented vertically, regardless the shape of the curve, which is useful in many civil applications, where this is maybe the alignment of a road or a tunnel or a bridge or any linear infrastructure per se. All right, so that was it. You could do this. We could do this in Python as well, but I showed this in the episodes regarding vectors, so you can go back and check those out. So this was it for today's video. I hope it was useful to understand better how extrusions, sweeps, and lofts work in Grasshopper and Python. If you did like it, leave a like and subscribe to the channel. See you next time. Bye.